Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 35 in series, and today we are going to discuss about hidden Markov models, and this topic we are already discussed, already we are covering from the last two lectures, and today we are going to discuss continuing that. And so, in the last class when you are discussing about the basic problems that are in HMM, there are three problems, and so the first problem used to solve efficient way of solving the probability of observation sequence given the model, that is P of O by lambda. And the second problem is that given the observation sequence and model and trying to find out the optimal state sequence that is generating the observation sequence. So, that is the second problem, and we need to find out the hidden state sequence from the given observation sequence for generating the observation sequence, the optimal sequence and all. And third one is that trying to estimate the parameters that maximizes the P of O by lambda. So, these are the three problems, and in the last class we tried to solve the first problem using a direct method. So, in that it was observed that using a direct method the number of computations that are involved is very huge. That depends upon like the n power t, like because at each instance we have n possible states. So, if the observation sequence length is capital T, so the number of possible state sequences will be like n power t, and for each state sequence the number of computations that are involved will be 2t. So, therefore, the total number of computations that are involved for computation of P of O by lambda will be like 2t times n power t. So, it is very huge by if you consider the numerically the sequence length equals to 100, if the number of states equals to 5, it is found to be like very huge in number or computationally very intensive. So, practically it is not possible to estimate P of O by lambda using a direct approach. So, therefore, we just discussed about another way of evaluating P of O by lambda. It is known to be like a forward procedure, and so this forward procedure consisting of like estimating the forward variable known to be alpha t of I, and here as I mentioned here. Here alpha t of I means here this is not capital T, this is assuming that some time instance t. So, alpha t of I indicates the probability of partial observation sequence. So, it means that you have observation sequence O1, O2, O capital T, and here the partial observation sequence means O1, O2, OT. At time t the system is in state I. What is the probability of the observation sequence O1, O2, OT at some time instant t? At that time instant the system is in state I. So, this is known to be alpha t of I, it is known to be partial observation sequence, that is probability of the partial observation sequence O1, O2, OT at time t the system is in state I, right. And then by using this forward variable approach, if you solve the if you try to solve P of O by lambda. So, it is nothing but here we have seen that the alpha t of I is nothing but the partial observation sequence till time t. At time t the system is in state I, the system is in state I. So, that way we can able to compute the estimate the probability at system I the state I at time t. So, that way here if you want to compute the suppose in the same way if you try to compute at time t plus 1, system is in state j. So, what is the probability of like the observation sequence at time t plus 1 system is j. So, this you can able to compute using recursion, like by using alpha t of I, there are like I equals to 1 to n. So, there are n possible states in the previous instance, and from that there is some transition probabilities to reach to the state j at t plus 1. So, this way if you try to evaluate this alpha t of phi at each time instant, you need the n computations are required, and at each instance we have like n states are there. So, therefore, at each time instant to compute alpha t of phi for all states where I varies from 1 to n. So, the number of computations that are involved will be n square at each time instant to compute the forward variable for all the states. So, the number of computations that are involved will be n square, because for each state it will be like n multiplications are required, right, and there are n states are there in each time instance. So, therefore, the total number of like computations that are involved at each time instance to compute the forward variable will be n square. So, likewise if you try to compute this forward variable at each time instant to reach to the end termination at capital T, the number of the multiplications that are required will be n square t, because at each time instant n square there are time instances, there are total t capital T of the sequence length. So, therefore, n square t computations are required. So, if you try to compare this n square t with like n capital T, n power t into 2t, like n square t is very nominal, like it means the example, if you consider the example the previous one, like if you take a 5 state model and if the sequence length equals to 100, then the using a direct method the number of computations that are involved will be around 10 power 73. It means 2 into t multiplied by n power t, n is 5 power 100, right, and if you try to evaluate that, it is close to about 10 power 73. It is a very huge number computations, it is computational intensive, and practically it is not possible. Whereas, by using this forward variable approach or forward procedure, you can able to see that. So, you can able to compute this alpha t of phi at each time instant for all the states, right. So, if you see that there are n square are required, n square computations are required at every time instance. So, there are total capital T time instances. So, therefore, the number of computations involved will be n square into capital T. So, here suppose n equals to 5 state model and capital T equals to 100, there are the sequence length equals to 100. So, that way if you try to realize the number of computations over here using forward procedure, the number of computations are roughly is about 2500, because n square is 25, 5 square into t is 100. So, 25 into 100, 2500. So, here using forward procedure we have 2500 computations, whereas by using direct approach you have seen that the number of computations involved will be 10 power 73, it is very huge in number. So, the similar way here there is a backward procedure. Here the backward procedure, where here the backward variable is defined as beta t of phi, and here the beta t of phi, the backward variable is defined just very similar to the forward variable, but here the observations are observed from the termination, whereas in case of forward variable it is a partial observation sequence from beginning, right, O1, O2, O3 up to OT, whereas here you can see beta t of phi is nothing but probability of observation sequence starting from t plus 1, t plus 2 up to capital T, given that at time t the system is in state I. Whereas, in case of alpha t of phi, the definition is that probability of O1, O2, O3, OT at time t, that is the system is qt equals to I. So, backward variable is just that is here the partial observation sequence, the probability of partial observation sequence from the end. So, that way here you can see the same way you can able to compute, suppose you are starting from the end. So, therefore, this beta t of I can be assumed to be 1 for all I. Then afterwards beta t of I is nothing but based on this definition, it is nothing but. So, beta t of I is nothing but here at from t plus 1 onwards we have observations, at time t the system is in state I, right. So, for reaching the state I at time t, so from t plus 1 the system may be in any one of the n states. So, therefore, here you can write bj of ot plus 1, bj of ot plus 1, and where here the system may be any one of the n states, j may be 1 to n, and multiplied by bj beta t plus 1 of j, it means that at time t plus 1 the system is in state j. So, that j may be any one of the n states. So, therefore, the summation of the product of this one beta t plus 1 of j and beta b of j of ot plus 1, and from this it reaches to I. So, the transition probabilities will be like aij, that means from j it has to reach I, aij, right. So, right from j equals to 1 to n. So, that way you can compute beta t of I is nothing but at time t the system is in state I, and by providing the observation sequence from ot plus 1 to ot. So, at ot plus 1 the system may be in any one of the states, any one of the n states, right. So, therefore, here the summation j equals to 1 to n, and this product takes care of that one, like the probabilities at this point at j plus 1 being in one of the states will be taken care by the bj of ot plus 1 is nothing but the is a symbol probability at time t plus 1, the system is at state j, system is at the state j, right, and the system may be in one of the n states. So, the j may be like 1 to n. So, therefore, j equals to 1 to n bj of ot plus 1, that is all possible symbol probabilities, and then the beta t plus 1 of j, it means that. So, from that point to the rest to the termination, and so that way this will be the summation over this product will take care about all of these things, and then multiplied by the transition probabilities. So, that way you can be able to compute beta t of phi. So, the same thing this applicable for all the time instances from capital T to like a t minus 1, t minus 2 till 1 you can able to reach. So, the same way analogy, the way we computed the way we have used the forward variable to compute the p of o by lambda, in the same way we can also compute p of o by lambda using the backward procedure also. And here the same again the number of computations that are involved will be the same number like n square t, the same analogy as we had discussed in the forward variable and all. And basically these forward and backward variables, these are used for estimating the parameters to solve the third problem and all. We will see that. Yeah. Before going to the solution to the third problem, we will try to see the solution for a problem 2. So, for a problem 2, we have seen that we observed that the problem 2 is that given the observation sequence and the modal parameters, we will try to find out what is the state sequence that best describes the given observation sequence and all. It is nothing but from the given observation sequence and the model. So, we need to try to find out what is the hidden state sequence that is responsible for giving this particular observation sequence. So, for that we have different approaches, we can do that, we can able to perform that in a different ways. So, one way is that suppose for example, if you try to find out the optimal state at each time instant, like because the observation sequence is O1, O2, O3, O capital T. So, if you try to find out the best state at each time instance, and then the sequence of those best states can be one of the state sequence that provides the best state sequence and all, right. So, it means that what I want to convey here is that at each time instant we will try to find out what is the best possible state at the time instant t, at time instant like from beginning like a 1, at time instant 2, time instant 3, time instant capital T. Likewise, at each time instant if you try to find out the best state at a particular time, because in a particular time there are n states are possible. Out of that, from the observation sequence we will try to find out what is the best state at a given time instant. Likewise, if you try to find out the best states at each time instant, and the sequence of those states can be viewed as the optimal state sequence in one way, right. So, for doing that, if you can able to we are here just defining the variable known to be gamma t of I, where gamma t of I is nothing but probability of the system at time t is in state I, gamma t of I. It means that this small t indicates that the time instant at time instant, right, and this the I that is within the braces indicates the state and all. It means that in the at time t the system is in state I. At time t the system is in state I. This t will be varying like 1, 2 up to capital T in case of discrete time instants, right. So, therefore, the gamma t of I is nothing but in a observation sequence what is the probability of the system is in state I at time t. The qt means nothing but the system is in state I, a system state at time t, that is equals to I for the given O of lambda. So, this you can able to compute as the probability of qt at time the state I and for the given O of lambda can be given as probability, this is nothing but can be written as the joint probability of observation sequence at time t, the system is in state I given the lambda divided by the probability of observation sequence qt of I given lambda, where the summation I equals to 1 to n. So, it means that here in the numerator we are forcing that the system is in state I, the system should be in state I at time t, right. The system may be in any one of the states, right. It may be like I equals to 1 to n possibilities are there. So, therefore, if you divide this probability with summation of all possible state probabilities, then that gives you the this one, the gamma t of I, right. Gamma t of I is nothing but what is the probability of the system in state time t is in state I, right. So, there are possibilities, the system may be in state I and the system may be the I may be any one of the n states, n possible states. So, therefore, if you perform this, that means if you compute the probability of joint probability of O comma qt equals to I with respect to the summation of the same joint probability with respect to all possible i's, then you can get the gamma t of I. You can get the gamma t of I. It is simple, right. So, the numerator, that means we are just trying to find out the number of times the system will be in state I at time t, and whereas the denominator is nothing but the that means all possible the states at time t, all possible states at time t. What is the number of times the system will be in any of the state, not only for I. So, that will be the summation. So, if you divide with that, it gives you the fraction of times the system is in state I with respect to the number of whatever the state it may be, right. So, that way you can write this the same thing, this is nothing but probability of O by lambda, right. The bottom one is nothing but probability of O by lambda, that means the system may be in any state, because here we are just forcing that the system is at time t, but at time t any state if it takes is nothing but probability of O by lambda. The denominator is nothing but probability of O by lambda, it is no constraint at all. And whereas the numerator we are constraining that probability of O by lambda, but provided at time t the system should be in state I, should be in state I. So, that way this you can able to write it as like in terms of forward backward variables, because at time t the system should be in state I, right, and then preceding and the following we do not have any constraint at all. So, therefore, this you can able to write it as alpha t of I multiplied by beta t of I. What is alpha t of I? Alpha t of I is nothing but probability of the partial observation sequence, like from 1, 2, 3 up to t, at time t it should be in state I, and prior to that we do not have any constraint at all, we do not have any constraint at all, right. And similarly, beta t of I is nothing but starts from ith state at time t, and then it continues the probability of like observation sequence from OT plus 1, OT plus 2 up to O capital T. So, that way the probability of observation sequence at time t being in state I can be written as forward variable multiplied by backward variable. So, this you can able to see here where here you can see here up to, for example, here at time t this is alpha t of I, right. So, there are different ways the state sequences are possible, but at time t it should be in state I, and here from here onwards if you take the like the rest and all, so then it will be like the other one is a beta t, right. The other one is the beta t, like if you look at the previous one, here you can see here this is nothing but beta t of I, right. This is nothing but beta t of I, right. So, it means that actually from here the system is state I, and then the observation sequence is available from OT plus 1, OT plus 2 up to O capital T. So, that way you can write the probability of the observation sequence at time t being in state I is nothing but alpha t of I multiplied by beta t of I, and the denominator is nothing but p of O by lambda. It means that there is no restriction of I can be any one of the states. So, there is nothing but the summation over I equals to 1 to n, whatever the numerator was there, alpha t of I, beta of t of I, this way you can able to do that. So, this way you can able to compute gamma t of I, and now as I mentioned that individually most likely state is nothing but among these alpha t of I is nothing but probability of the partial observation sequence or probability of observation sequence at time t the system should be in I, and likewise you can able to compute these gamma t of I for various i's. So, among that suppose whatever the maximum is there, so that is nothing but the maximum, the most likely state at time t, right. So, that is nothing but you can able to compute by using arg max I of gamma t of I. It means that here gamma t of I is nothing but the probability the system being in state I, and if you can able to compute all probabilities the system being in state I where I equals to 1 to n, among that here the gamma t the qt star is nothing but we are picking up the best state, that means the maximum probable state out of n states at time t. So, that way if you can able to perform for every time instant, then it is nothing but then that particular sequence is nothing but the maximum likely states at each time and all, right. So, that is one way to compute the state sequence, but in the domain of speech that particular state sequence may not be valid, because here in the speech production where the state sequence are nothing but the sequence of vocal tract shapes, right. So, the vocal tract shapes it will follow in only one direction, because if you see that for a vowel vocal tract shape, that depending upon the shape of the vocal tract we have different states are possible. Suppose vowel is there where the vocal tract will be first at the closing state, then afterwards it opening, and then it reaches to maximum opening state, and afterwards it tries to and then it retains that. So, it means that the vocal tract shape follows only a particular sequence of shapes, that means starting from closing, then opening, then the opening will be increased, then it reaches to maximum opening and retains there. So, those are the state sequence of states that is responsible for the production of vowel a. Likewise, for different sound units it has a different sequence of shapes. So, but here when you are computing this maximum likely state, we are considering all possible states. So, whereas in case of speech production or in the context of a speech, all transition probabilities may not exist. There are only some legal sequence of states are permissible. So, therefore, if you look at the state transition matrix of in the context of speech for production of speech, where it is not that the entire n cross n matrix is not non-zeros. There are certain state sequences that are not permissible. So, therefore, they will be 0. That means, there are some 0 values used to be there, that means, there are certain values aij will be 0 in the state transition matrix, right. And so, therefore, in this in view of that, here this that means the chances of the individually the most likely states at each time instance may not be the valid sequence at all sometimes. So, therefore, in the case of speech we cannot consider that this way, like most likely states at each time instance. And there are different applications. There are certain applications where the state sequence will be considered as the maximum expectation of the pairs of a states. It means that suppose there are like the sequence length is t, then we will try to find out the best pair the maximum expectation or the most likely the pairs we will try to compute in the sequential way, and then that way we can able to estimate the best sequence. And likewise, sometimes you can try to compute the maximum probable triplets. It means that actually suppose triplet means you have to find out the t minus 1, t plus 1. Likewise, at each instance we will try to compute the triplets, and then we will try to find out the best sequence in the form of triplets, sequence of triplets. And whereas here these three are nothing but the first one is nothing but the individual states, the second one is nothing but maximum likely pairs of states, and the third one is nothing but maximum likely triplets. But in the case of a speech we cannot consider these things, because some of these things may not exist at all, because it is not that all possible state transitions are not permissible, right. So, therefore, in the context of a speech the best state sequence means we need to find out the entire state sequence, like, and then from that we will try to find out the best state sequence and all. So, that way we can able to evaluate the best state sequence using the dynamic programming, it is known to be Viterbi algorithm. So, using a Viterbi algorithm, we will try to find out the optimal state sequence. So, here we will see that how do we find out the optimal state sequence by using a Viterbi algorithm, and for that here we are considering another variable known to be like delta t of I, delta t of I. So, here the delta t of I is nothing but is a maximum the probability of like O1, O2, O3 partial sequence, like at time t the system is in state I. So, here what we are doing here is that this is similar to the forward variable, but in case of forward variable we are just estimating the probability of the partial observation sequence at till time t. At time t the system is in state I, right, and whereas here in the case of here in this case delta t of I is nothing but there are several state sequences are possible to reach the at time instant t, the system being in state I. There are several possible sequences in which the sequences may terminate at time t at state I. And here what we are doing is that among those several sequences we are trying to find out the maximum sequence, maximum probable sequence. There are several sequences that will terminate at time t with state I. Among those several sequences, what is the maximum probable the state sequence that is terminating at time terminating to the state I at time t. So, that is nothing but the maximum probability of q1, q2, q3, qt minus 1, right. What is the maximum state sequence, maximum probable state sequence q1, q2 up to qt minus 1, and at time t the system is in state I. That means, at time t there is a system should be in state I, and what is the probable, what is the maximum probable state single state sequence that is reaching to state I at time t. That is what is the definition of delta t of I, delta t of I. So, by using induction you can able to compute the next time instance, that means delta t plus 1 of j can be computed using induction the same way we have done. It means that because here the delta t plus 1 of j is nothing but the maximum probable single state sequence that is terminating to a state j at time t plus 1, right. So, this we can able to do it using induction. It means that actually at time t plus 1 the system should be in state j. So, therefore, at time t the system will be in one of the n states. Out of those n states, which is the maximum probable state. So, that way you can able to compute. Here it means that alpha gamma delta t of I, it means the delta t of I there are like I may be like 1 to n, it may be varied. Out of that we need to find out the maximum delta t of I, the maximum delta t of I, that is from that we have to reach to the next state, we have to reach to the next time instant, the state j at the next time instant. So, therefore, here we can able to compute delta t plus 1 of j is nothing but what is the maximum probability of a single state sequence that is reaching to a state j at time t plus 1. So, for that what we are doing is that we are doing by using induction recursively delta t of I, right, and then transition probability of ij aij. So, among these, because in the previous time instant whichever is the maximum product of this one, right, there are n possibilities are there. Out of these n possibilities whichever is the maximum. So, that from that particular state we need to reach to the like state j in the next time instance, right. So, for that what is that maximum I? So, that is used for tracking the state sequence and all, because at time t plus 1, suppose from this if you want to backtrack that particular state sequence, that means for reaching to this t plus 1 we will try to see that what is the maximum of these products of n products. From that we will try to find out the preceding state, the preceding time instant, what is the maximum probable state, and then again from that again we have to backtrack, then what is the next maximum probable preceding state. So, likewise if you keep on backtracking, then you can able to find out the single state sequence that gives you the maximum probability to reach to the state j at time t plus 1. So, that way here you can see that for backtracking that one, we use the a variable known to be like a psi t of j plus psi t of j. It means that it tries to like find out the state at time t to reach to the state j at time t plus 1, because at j the state j at time t plus 1, and for that what is the maximum probable preceding state to reach to the state j, and for that we are computing here like gamma delta t of I into a I j, and here from this like there are like n different possibilities. Out of that, whatever is the maximum of this product, so that particular state, from that state it has to reach to the state j at time t plus 1, right. So, therefore, this is valid for t equals to 2 to capital T, like from 2 to capital T, and j equals to 1 to n for all possibilities. This is, so that way you can able to compute this delta t of j for all possible j's and for all possible t's, for all possible j's and for all possible t's, and from that we will try to find out what is the maximum, and from that we need to backtrack. So, here with this by using this definition, we will start with the initiation. At the initiation step, gamma 1 of I, it is nothing but gamma 1 of I is nothing but, it means that at initial state the system is being state I, right, and that is the probability of that is nothing but pi I into b I of O1. Pi I is nothing but the initial state probability system being in state I, that means that I may be any one of 1 to n, and multiplied by the symbol probability b I of O1, right. So, with that you can able to estimate gamma 1 of I, right, we can able to estimate that, and here since it is the initial state, there is no backtracking is required. So, therefore, the psi 1 of I equals to 0, because there is no backtracking, because this is the initial state, right, and so therefore, we cannot anything backtrack from that. So, therefore, this is a starting point. So, therefore, psi 1 of I equals to 0 for all i's, and then recursion, that means delta t of j is nothing but max of I delta t minus 1 of I into a I j of b j of o t. Just similar to this definition is just exactly the same thing. Instead of t plus 1, this is just t. See that the delta t of j is nothing but max of I delta t minus 1 of I into a I j of b j of o t, and this is valid for t equals to 2 to capital T. So, by using this recursion you can able to just move forward at every time instant, and for every state you can able to compute that. And then for backtrack of this one, that means to reach to the whatever the maximum of this one, this index will be stored by using this one, the psi t of j. The psi t of j is used for like for the state j at time t plus 1, right, and for that what is the maximum possible state at time instant t, what is the maximum max probable state at time t, right. So, that way you can able to for all j you can able to compute, right, and so using the psi t of j you can able to find out for every j, for every state at time t plus 1 what is the maximum probable state. So, that way you can able to compute this one. Psi t of j is nothing but like delta t minus 1 of I into a I j, among this whatever the maximum. So, that is be stored at a psi t of j for different values of j, right. And so, now based on that way if you keep on computing that, then finally you reach to the delta t of j, delta capital T of j. It means that we are reaching to the end, and that delta capital T of j is nothing but again the same thing, same recursion, you can use it like max of I of delta t minus 1 of I a I j into b j of o t. And once you reach to this, likewise here you see delta t of j, where j equals to there are m possibilities, m states, like j equals to n states 1 to n. So, delta t of 1, delta t of 2, likewise delta t of capital N you can compute. Out of that whatever the maximum of delta t of I, so that is the final state of the optimal state sequence, final state of the optimal state sequence. So, from that you can able to find out the maximum delta t of I. From that you need to backtrack, So, therefore, here the final at the last time instant whatever the state in the optimal state sequence is nothing but max I of delta t of I. Like there are n possible states in the last time instance, out of that whatever the maximum delta t of I is there, that will be that particular state is happens to be the last state of the optimal state sequence, and from that you need to backtrack. So, for reaching to that, what is the maximum probable state in the t minus 1, that you can able to compute by using this this psi of t. By using this expression you can able to backtrack that one. By using this expression you can able to backtrack this one. So, by using this delta t of j, for every time you will use to compute, and each time whatever you compute, we need to track that the preceding state, whatever the max probable state for reaching to this particular state at this time instant. So, that way this psi of t of I used to capture the preceding the state the preceding time instant, what is the maximum probable state to reach to this particular state. So, that way using this expression you can able to compute. So, that way you can able to, after reaching to the termination, then you can able to backtrack by using this expression, right, and with that you can able to find out the optimal state sequence and all. So, this way in the problem 2, for a given observation sequence and the model, you can able to compute the optimal state sequence. And this is the Viterbi algorithm, and so is proposed by this algorithm is used actually in coding theory, and so the similar algorithm or the same algorithm can be used here also for the tracking the states in the case of optimal state sequence. Yeah, now we will try to look at the problem 3. Like as you know that the problem 3 is nothing but it's a training step. It's nothing but estimation of the model parameters A, B, pi. What is A? A is nothing but a state transition matrix. B is nothing but the symbol probability matrix, and pi is nothing but initial state matrix, right? And so here how do we compute this? For computation of these things, we use the iterative approach. Because directly estimation of that it involves a lot of nonlinear solving the nonlinear equations, the coupled equations and all. It is very difficult to solve that nonlinear equations, and so therefore, the better approach is that using iterative approach. So, the iterative approach we are already familiar with that, like we know that initially we will assume some parameters, then afterwards we will try to update those parameters using the data for maximizing the posterior probability. Alright. So, that way here for doing that, here we are assuming one more variable known to be, you can say, the psi t or eta t of I j. It is nothing but the definition of this is nothing but probability of the system being at time t, it is in state I, at t plus 1 it is in j, given O on lambda. Means that eta t of I comma j, it indicates that at time t the system should be in state I, and the next instance the system is in state j, right, given the observation sequence and lambda. That means, given the observation sequence O1, O2, O3, O capital T, in that we need to find out what is the probability of system being in t and t plus 1 having the states I and j, a pair of states, right. So, whereas gamma t of I is nothing but the system being in state I at time instant t. That means, at a particular time instant, what is the probability that the system is being state I, and here in a successive time instance, what is the probability that system is being state I at time t and j at time t plus 1, right. So, this is nothing but again the joint the same way, the way we computed for a gamma t of I, you can also estimate the same way. And here the joint probability of observation sequence and the system will be in state I and j at time t and t plus 1, given the lambda, divided by p of O by lambda. That means, there is no restriction at all. The system being any of the state at time t and any of the state at time t plus 1. It is nothing but p of O by lambda, right. So, here this is the case where we are just imposing the constraints at time t and t plus 1 such that the system should be in state I at time t and the system should be in state j at time t plus 1. That is the restriction or constraint that we are imposing that, whereas in the denominator we are releasing that, we are not no constraint at all. So, that means all possibilities are there. So, therefore, by taking this fraction division, we can get the probability of the R, we can get the the eta of t I j. That means, what is the probability of the observation sequence visiting the state I and j at time t and t plus 1 instances, right. So, this is the one you can see, this is the way. See this is the one, like you can say this is observation sequence O1, O2, O3, OT minus 1, OT, OT plus 1, OT plus 2 and so on. And here the constraint is that at time t the system is in state I, and at time t plus 1 the system should be in state j. And then for doing that, there are several sequences that are reaching to state I, and then there is only one possibility that it has to go from I to j, and afterwards from j it can reach to it can go to any one of the states at a later point of a time. So, this you can able to formalize in the terms of like forward and backward variables, this way. Here the probability of the joint probability of O comma the qt equals to I and qt plus 1 equals to j can be written as alpha t of I is nothing but the probability of the partial observation sequence at time t system being I, right, and then bj of ot plus 1 is nothing but at time t plus 1 the system is in state j, and then for moving from I to j the transition probability is aij. So, therefore, alpha t of I into aij into bj of ot plus 1, and at bj of ot plus 1 the system is in the symbol probability is nothing but the symbol probability, the system beta of t plus 1 of j, and the symbol probability is bj of ot plus 1. So, that way the numerator part is nothing but the system is visiting states I and j at time instants t and t plus 1, and the denominator is nothing but no constraint at all. That means, there is no restriction on the system should be in state I and j at t and t plus 1. So, therefore, all possibilities of I and j's can be considered. It is nothing but summation of all possible I and j at time instants t and t plus 1, right. So, this is the denominator. So, using this you can able to compute eta t of I comma j, right. Eta t of I comma j and gamma t of I, they are similar. Gamma t of I means just we are constraining only at a particular time instant, whereas eta t of I comma j means we are constraining the sequence at the successive time instants t and t plus 1, where we are imposing that at time t the system should be in state I, and at time t plus 1 system should be in state j. And now, by using this, once we have gamma t and eta t of I comma j, we can able to compute the parameters a, b, pi using the following way. You can say gamma t of I can be written in terms of again eta t of I comma j, because eta t of I comma j means we are restricting at both time t and t plus 1 I and j. And suppose if we restrict only at time t and at t plus 1 if we want to release, it is nothing but at t plus 1 we are restricting to j, but if you consider all possible j's is nothing but it is nothing but again gamma t of I, right. So, therefore, you can write gamma t of I in terms of eta t of I comma j as summation of eta t of I comma j, where j equals to 1 to n. And now, if we try to compute the parameters here, the average number of transitions from system I can be written as state I. Here gamma t of I is nothing but the probability of system being state I at time t. So, likewise, suppose we want to compute in a state sequence how many times the system is visiting state I, because state sequence like O1, O2, O3, OT, suppose there are 100 observation sequence, 100 observations are there. So, here the question is that how many times the system or how many times the state I is visiting in the total number of observations, how many times it is visiting I. So, that you can able to compute, like at each time instant we have a probability, we know that gamma t of I. So, if we sum this probability for every time instant, time t equals to t minus 1, right. So, then we can able to get the system is in state I at different times t's, right. T equals to 0 to like 0 to t, it is not t minus 1, it is a capital T, like t equals to 0 to t equals to 1 to capital T, because our interest is that at time instant t the system should be in state t. So, average number of transitions from state I will be, it is nothing but here t equals to 1 to t minus 1 gamma t of I, right. Here, here it will be like what is the here it is nothing but what is the average probability or average number of times the system is visiting the state I, right. System is visiting state I, and similarly you can able to find out the average number of transitions from the system is passing through states I and j at times t and t plus 1, right. So, here in the previous one it is nothing but what is the average number of transitions of the state I in the observation sequence O, and here is nothing but average number of transitions from I to j in observation sequence. It means that it is a pair, we are just trying to compute the all possible pairs of transitions I to j in the observation sequence. Again the same way you can able to compute, know that I to j transitions can be captured by using eta of I j. So, therefore, eta t of I j where t varies from 1 to t minus 1. So, if you sum up all of them, then you can able to get the average number of transitions from I to j, average number of transitions from I to j, right. And so, here it is like a t because it is only one state. So, therefore, it reaches to even the final state also can able to consider how many times the system or the observation sequence may visit the state I in the last state. It is a chance, it is possible, but here you cannot do that because when you reach to the last state there is no further state. So, therefore, we need to conclude or we need to stop at t minus 1 itself. So, now by using these formulations you can able to compute estimate the expected number of initial state probabilities, that is pi I bar, you can able to write that as a gamma 1 of I. It means at time t equals to 1 gamma 1 of I, that way you can able to compute the pi I bar. Pi I bar means initial state probabilities, initial state probability you can able to compute gamma 1 of I, right. It is nothing but what is the maximum probability the system being in state I at the beginning. Likewise, for each I you have some maximum or probability will be there. So, all those probabilities will form the pi I bar. Similarly, Aij bar is nothing but the transition matrix, it is nothing but the expected number of transitions from I to j to the expected number of transitions from I to anywhere, right. So, this can be done, this is nothing but right expected number of transitions from I to j by expected number of transitions from I to anywhere, right. So, this fraction gives you this one. So, this is nothing but gamma t of I j where all t's summation over all t's divided by this is eta and this is gamma t of I, right. So, this by this fraction you can able to compute the all Aij's. Likewise, the Bj k cap is nothing but the symbol probability, it is nothing but what is the probability that the system is in state j having the symbol of Vk, right. So, this you can able to compute the expected number of times the system is in state j and the OT equals to Vk. OT means the symbol will be happens to be the particular the vector, a particular observation to be a particular symbol and all. So, this is the joint probability of, we can write joint probability of the system being in state j and the symbol will be like OT equals to Vk. So, that you can able to write this way like gamma t of j gives you the what is the probability that the average number of times the system is visiting state j, right, but at that state the probability the OT will be Vk. So, therefore, this is a conditional way of you have to estimate this one, right. So, this gives you the what is the average probability or average expected number of times the system is in state j, and at state j the symbol should be like OT should be Vk. So, this is the conditional one. So, therefore, this way you can able to estimate this one divided by without imposing the condition, that means without imposing the symbol condition and all, that means gamma t of j where t equals to 1 to capital T. So, that way you can able to compute the symbol probability and all. So, using these expressions you can able to estimate the symbol probabilities. So, how do we do that? Again, it is an iterative approach as I mentioned that. So, we will start first with some observation, some random observations, guess, and afterwards using those observations and by observing the data we can able to estimate this, and now this becomes a new parameters, and using this new parameters we will try to estimate the like by observing the data again we will try to find out that, and each time when you try to compute we will try to see that what is the P of O by lambda for that model. So, likewise every time when you try to estimate these parameters. So, with these parameters we will try to find out what is P by O by lambda bar. If P of O by lambda, P of O given lambda, the new lambda, if it is always should be greater than the older one. So, as long as this is improving, so we have to keep on continue the iterations, and whenever the improvement of this P of O by lambda bar compared to P of O by lambda previous one is not significant, at that time you can stop and you can say that the parameters are optimized and all. After computing this gamma T of I, where you can see that gamma T of I is nothing but a probability of in the observation sequence at time t the system should visit I, and this you can also compute in terms of eta t of I comma j, as we have mentioned, because eta t of I comma j means here we have a constraint where the successive states should be I and j, and if you remove that constraint the j, so nothing but if you take the all possible values of j, then it is nothing but equal to gamma t of I, and then you can able to compute the average number of transitions the observation sequence visiting the state I can be written as like a summation over t equals to t minus 1 gamma t of I. So, likewise you can also compute the average number of transitions the state visiting I to j, and then these parameters the like initial state probabilities, state transition probability and the symbol probabilities, you can able to estimate in terms of this gamma t of I and eta t of I comma j, eta t of I comma j, you can able to compute that. And so, here you can see like after computing these parameters, here as I mentioned that here the parameters are estimated using iteration approach. It means that initially since we have no idea, so therefore, this AB pi, that is a state transition matrix, symbol probability matrix and initial state transition matrix, initial state probability matrix. So, they will be taken some arbitrary values and use those arbitrary values, and then by looking at the data observation sequences, and you can able to estimate these alpha gamma t of I and eta t of I, and then by using this you can able to estimate the parameters from the data. And once you estimate the parameters from the data, and those parameters are happens to be your new parameters, like updated parameters, and using these updated parameters we will try to find out P of O by lambda for the training data for the all possible all possible observation sequences. And for all of them, if you compute, if you take average of that, and if that P of O by lambda bar, that means probability of observation sequences, that is nothing but the training data for the given new parameters, if you try to estimate that, and we will try to compare with the older one. So, if it is greater than the older one, then we can say that yeah, the parameters are better, and we will continue for iteration. Likewise, these iterations will continue till whenever the P of O by lambda bar is not significantly different from the P of O by lambda. At that point, we will stop the iterations, and whatever the parameters are there, A, B, pi, so those are known to be like optimal parameters for the given training data. So, that way you can able to estimate the parameters. Then coming to the types of HMMs, as we have seen so far, the HMMs that we are considered were there are the depending upon the state transition matrix, the structure of state transition matrix, the HMMs can be broadly categorized into ergodic and left right HMM. Ergodic HMMs, the HMMs that whatever we have considered, it means that suppose if there are n states are there, and if the entire state transition matrix contains all non-zero values, it means that from any state to you can, there is certain probability you can able to reach to some other state. So, that is known to be ergodic HMM, and so the other one is a left right HMM. So, in case of ergodic HMM, as I mentioned, that is a fully connected HMM. It means that for all Aij is greater than 0. It means like all that means the Aij matrix, that is a state transition probability matrix, all values, that is all n by n values, they are greater than 0. It means that from each state you can able to reach all other states, right, with certain probabilities, right. And so, this is known to be the fully connected HMM or the ergodic HMM, and the other one is known to be the left right model or the Bucky's model. So, where as I mentioned that in case of the speech processing or the speech production mechanism, so as we have seen here the HMM is nothing, the states of the HMM are nothing but vocal tract shapes, And as we know that for a speech production, the vocal tract shapes will take the different shapes in a systematic way. Like for example, as I mentioned, for the production of vowel a, the vocal tract first starts from the narrow state and then it will open and then keep on increasing and then it reaches to maximum opening state. That is the way the a is modeled, the vowel a is produced. Like for example, ka, for example, where there is a constriction in the vocal tract, that becomes one of the state, and afterwards release of a constriction and then air passing through that. So that way you can able to view this vocal tract shape like in a systematic way, like the sequence of vocal tract shapes, it follows some systematic manner. It's not that all these vocal tract shapes cannot be reached from one to another with all possibilities. So what I mean to say is that in case of production, speech production, our vocal tract shapes will follow a forward sequence. It means that after some middle state it cannot reach back. It means that for production of vowel a or whatever, from narrow state, from narrow opening and then we are going to the wide opening, and it's progressively it's moving and the vocal tract shape is keep on increasing, right. And so that way in the case of while modeling the speech, it's better to have like the state transition probabilities or states visiting will be like it is in the forward direction. It means suppose if we start from 1, the system can move back to the state 1 and then or otherwise it may go to the state 2 or it may go to the state 3. Like suppose for example, when you are in state 3, the system cannot move to the previous states, right, because as we have seen that in the speech production our vocal tract shapes are move only in the forward direction, right. So that way in case of left right model, so Aij will be 0 when j is less than I. It means that the reverse arcs will not present. That means here the states will not go backward, only in the forward direction, or it will go it will be in the self transition, it cannot go backward. So that way Aij equals to 0 for j less than I, right. And then coming to the initial state, the system should start from the initial state. It cannot start from like the initial vectors cannot start from state 3 or state 2 and all. So therefore, if you look at the pi I equals to 0 for all I which is not equals to 1, that means that the initial state should start from the first state only. So therefore, pi I equals to 0 for all states I not equals to 1, and it is pi I equals to 1 when state I equals to 1. So it means that all initial states start from this and then keep on move, right. So therefore, these are the restrictions that are on constrained or that are imposed on the left right model, and this was proposed by the researcher known to be Bucky. So therefore, known to be Bucky's model and all. Bucky's model. And likewise in this left right model, depending upon the domain or depending upon the problem, we can impose the restrictions. Suppose for example, here in this case it is a left right model, and again we are imposing the restriction that from one state it can able to transit maximum 2 states away from it, not more than that. You can see that Aij equals to 0 for j greater than delta I plus delta I, where delta I equals to 2. That means that from any state it can move maximum 2 states away from it, not more than that. Here in this case 3 state model, if you look at that, from state 1 it can reach to state 3 maximum, like it cannot reach to state 4 directly, right. So that is known to be like that depending upon the system or underlying data what you are modeling. So based on that you can impose the constraints and all. So this is known to be left right model, where the arcs, or you can say the transitions are only in the forward direction, and that too in the forward direction also it just only transit only the 2 states away from that. And and again in HMMs, so far whatever we discussed, they are the discrete HMMs. It means that the observation sequence is to be some finite alphabets or a finite symbols and all, right. So whatever we have seen, even though we are modeling this the speech using HMM, and the spectral vectors that are extracted from a speech signal directly, it is a continuous in nature. It is continuous, but to make it discrete we are passing these continuous speech vectors, spectral vectors, through vector quantization codebook, and based on the size of the codebook, the number of symbols are limited. Suppose if you are using a vector VQ codebook, vector quantization codebook of size 1024, then the output, the observation sequence or observation symbols will be maximum 1024, only 1024 only, but the input will be continuous. But when you are using that the discrete HMM or sometimes the discrete feature vectors, there will be some loss of information obviously, because the continuous spectral vectors we are quantizing using a vector quantizer. So, in that process sometimes there will be certain loss that will be involved, and that loss, that depending upon the problem we can consider, or we can tolerate that loss sometimes, and sometimes that loss will be significant. With that, the accuracies or the target applications may not be achieved at all. So, in that case we need to, instead of going for a discrete HMM or discrete symbols, we need to go with the continuous feature vectors itself. So, if you use the continuous feature vectors, then we need to design the HMMs accordingly. So, the corresponding HMMs are known to be like continuous HMMs. So, in this case the methodology or like overall perspective remains same. The only difference here is that the states are represented by a continuous feature vectors. Earlier the states are the discrete feature vectors. So, therefore, the states are represented by the distribution, probability distributions, whereas here since it is a continuous feature vectors, so the probability distribution or the states are represented by probability density function, continuous density function. So, here again for a probability density function to represent that one, so each state is represented by like a mixture models, right, using a mixture model. So, therefore, here you can say that Bj of O, it is nothing but here the state j we are representing. So, the state j is represented by a mixture model with with m components, a mixture model with a m components. So, you can see that Cjk is nothing but a mixture coefficient, like a mixture coefficient for a kth component Cjk. Likewise, we have m components are there. So, therefore, Cjk is nothing but a mixture coefficient, and then this n of O comma mu jk and this psi jk, this is nothing but covariance matrix, and this is the mean vector and all. The mean vector corresponds to the kth component of the state j. That means, the state j is realized by the mixture model, where the mixture model contains the m components, and those are indicated by k, where k varies from 1 to m. So, that way the Bj of O, that is a state probability or a state symbol probability, that means in a given state what is the symbol probability, that is indicated by this one, like Bj of O can be indicated by Cjk is nothing but mixing coefficient, and these are nothing but mean vector and a covariance matrix, right, of a kth component. And so, here the same thing applies over here also. Cjk is a mixture coefficient, there are m components. So, therefore, Cjk summation over k equals to 1 to m equals to 1, and Cjk will be greater than 0. It is like, since it is a probability for all components, the probability will be greater than 0, and j and k are varies. J is nothing but state. So, therefore, it varies from 1 to n, and k is nothing but the mixture components, is varying from 1 to m. And so, these things, they are the symbol probability will be 1 in the integration limits like minus infinity plus infinity. And now, by using that you can able to estimate the these probabilities, the state probabilities and all. Like you can say Cjk can be estimated using this, because we know that how to compute gamma t, right. Gamma t, earlier it is a gamma t of j only, and now here since it is like a mixture, you are realized with a mixture, like. So, therefore, there are, it is also including that also, like a gamma t of jk, it is nothing but like the partial probability, the system being in state j and in the kth component. So, therefore, you can see that this Cjk, mu jk and this covariance matrices, they are computed using gamma t of jk, right, and the summation here for all t symbols, and this is for all components. So, that way you can able to compute Cjk bar and the mu jk mean vector covariance matrix you can able to compute. And again gamma t of jk can be computed here this way, like gamma t of jk is like similar to gamma t of I, this is the way we compute, right. And here the second factor that includes the further computation, like computing the other components and all, right. Here this is the one what we have seen, gamma t of I can be computed using this, the first factor, right. And here since it is a continuous HMM where it involves the mixture model. So, therefore, the second factors which includes that the state that is represented by a mixture model and all. So, it is nothing but Cjk multiplied by Cjk is nothing but the mixture coefficient, right, for each component, where k refers to the component, and then this is nothing but the probability, the model with a mean vector and a covariance matrix and all. And there are m components. So, therefore, here this is for kth component and this is for like the denominator is nothing but like a summation over all m components, all m components. So, that way you can able to compute gamma t of jk, and once you have gamma t of jk, then you plug in this gamma t of jk in these things. So, that way you can able to compute the with respect to state which is represented by mixture model, those mixture parameters you can able to estimate, you can able to compute like this way, like C jk bar, mu jk bar and the sigma jk bar. So, this way we can able to estimate the like the HMM parameters in case of continuous feature vectors, whereas the one whatever we have discussed so far is the HMM parameter estimation for the discrete symbols, whereas in case of continuous case we can able to just the only variation what we observed here is that the state here is represented by a continuous density function, continuous probability density function realized by the mixture models, right. So, other than that the discrete HMM and continuous HMM remaining all properties characteristics remain same. The only difference is that the state representation, where earlier the state is represented by using distribution, probability distribution, whereas here the state is represented by a probability density function realized by the mixture model and all. Thank you.